Hello, my name is Marco Paniconi, and thank you very much for inviting me to give this talk. Um, I work at Google in the video codecs team, in particular on video codecs for RTC applications. I am the TL for the video codec RTC work for AV1, also for VP9, and also going back down to the VP8 days. We work closely with the WebRTC team in trying to get the video codecs into the Google products, namely Meet and Duo. So this talk will be an overview of the libaom AV1 encoder, and I hope it will be useful for people who are interested in using it in their RTC applications. So the outline of my talk will be, I will first emphasize the encoding mode that we use for RTC applications, and then a brief selection of the features and coding tools. I'll then discuss the use cases for RTC, which is namely Duo and Meet, along with the work we did to get AV1 into Chrome. And then I will talk about command line and settings, followed by some comparison results. I want to conclude by touching on two topics for RTC. One is SVC, and the other is screen share. Okay. So for the encoding mode, I just want to clearly state the encoding mode. RTC applications, real-time communication applications require fast, low latency encoding with good rate targeting. So for this, we use the following encoding mode: one-pass encoding, real-time mode, which just means that this real-time mode will map into an internal set of speed features that allow for real-time coding. The lag in frame parameter is equal to 0. That means there is no future references, so all the references are in the past. And we use CBR rate control. This allows for tighter rate targeting. This is done for also the one-layer and the multi-layer case. This is basically to avoid overshoots, and especially in the multi-layer case, to be able to try to hit the target bit rates for each spatial temporal layer. Some of the main coding features and tools we use for RTC. The first is a quality CPU trade-off setting that we call it the speed setting. It's denoted by CPU used in the command line. And the range for RTC is 5 to 10, speed 5 to speed 10, with the higher speeds being faster encoding, but lower quality. Another feature I want to mention is, of course, encoder multi-threading. And in AV1, we have tile-based multi-threading for both column and row tiling, where the minimum tile size is 1 superblock. And we have row-based multi-threading within a tile, which is set by the row MT parameter equal to 1. Typically, depending on the content and so on, typically we can see about 1.8x speed up in going from 1 to 2 threads, and around 3x speed up in going from 1 to 4 threads. Another feature is the layered coding, or the SVC coding, and where up to 8 temporal and 4 spatial layers are supported in AV1, and I'll talk about the SVC a little bit more later on. We have a temporal denoiser in the RTC encoding path. This is used to remove camera noise. This is something that's been very useful in the past codecs, in the VP8, VP9 codecs. And the last item on this slide is I want to mention the compiler build flag to reduce the binary size. It's denoted by real-time only. And we use this to reduce the binary size, and this was important for getting AV1, software AV1, libaom AV1 into Duo and Chrome. Okay, so I'm going to continue on the next slide with some more selected features and coding tools. These are ones that are more related to quality and rate control. So AV1 uses variable block sizes like VP9, but there's more partitions available in AV1, and in particular, we can go up to 128 by 128 block size. CDEF is used for RTC, and this is a component of the loop filter, and it provides good visual quality at low bit rates. AQ mode is a feature that allows for setting the QP level at the coding block level via segmentation. For RTC, we use AQ mode equal to 3, which also gives good quality gains for video conference material. Compound prediction is used in the RTC. This is, of course, using past references because the lag in frames is 0. And the kind of fast version of it is implemented in the higher speeds, speed 7 and above. For screen content, AV1 has a lot of unique, useful tools for higher coding gains, and in particular, we are using the palette mode, and I'll mention this a little bit towards the end of the talk. And lastly, dynamic resize is a useful tool for RTC applications, which is used to get better quality and rate control at very low bit rates by reducing the resolution, the spatial resolution. And in AV1, also as in VP9, this can be done on the fly without issuing a keyframe. Okay, the main use cases for AV1 RTC is Duo and Meet. Duo is a mobile application, and Meet is a web and mobile application. For these applications, low complexity encoding is obviously needed because of limited CPU resources, and battery usage is an issue. Also, low bit rates are very important for mobile, and I just have here on the slide a few stats that shows roughly the percentage of mobile calls in the US in different locations. And you can see that the cost of the bandwidth is a very important issue in many locations. So for Duo, the libaom AV1 encoder was specifically used for low resolutions and low bit rates. Low resolutions meaning quarter VGA and below, and bit rates when it were as low as 20 to 30K. libaom AV1 in Duo was released around August, September 2020. In the next slide, this was just an announcement, the link to the announcement about it in 2020. About the upcoming release. And, there's been really since then, we've gotten a lot of good feedback, and it's been a really big improvement for users with low bandwidth. In the next slide is just a quick example of a video quality side by side, comparing AV1, RTC on the left, and on the right is the reference quality that was used in Duo. So AV1 is on the left, and you can see the big difference in video quality. For Google Meet, the first big step was to get AV1 into Chrome, and this was done in M91, which was just about a year ago. And since that milestone, there have been many quality and speed improvements that have been made. Currently, one can do one-to-one video calls with AV1 using app RTC. I have a link here to the deployment guide, and also the URL parameter that you need to set to actually enable AV1. WebRTC and Chromium is actively using AV1, testing it, and I put the encoder wrapper link here. So here you can see all the generic RTC settings that are used. And also, since the launch last year, we've been working hard in getting SVC fully supported, and it is currently fully supported in Chrome SVC for AV1. So it's actively being tested for Google Meet and for various different scenarios, encoding configurations like single layer encoding, multi-layer, which means with temporal or spatial layers, and also for screen share, which is a screen content mode. I also want to mention the web codecs, and there's a link here to that, is also recently added support for the AV1 RTC encoder. Just a few more points about AV1 in Chrome. The RTC encoder is available in Chrome for Linux, Macs, and Chrome OS. A lot of work went into reducing the binary size to get it in. So as I mentioned, there's a build flag called real-time only. And this is used to remove complex tools and code that are not needed for real-time. So we had some big reductions in binary size with that flag that were needed for the mobile and the desktop. Additional build flags for RTC in Chrome are high bit depth is set to 0. And building with temporal denoiser is enabled, so that if they want, the user can enable temporal denoising. It's off by default in WebRTC, but it's an option. And for the decoder, the David decoder is available on Chrome. It is or will become available very soon in WebRTC as well. Now, Meet uses hardware encoders when required for performance reasons, or like CPU overuse or overheating. So for hardware encoding in Chrome, we have provided in libaom a rate control interface to allow hardware encoders to use CBR rate control as it's used in the software RTC encoder. So in a sense, we externalize the internal rate control into a separate component that could be used by hardware encoders that are operating in constant queue mode. So this enables hardware encoders in Meet to achieve much better rate targeting, especially for layered encoding. So this is supported for both one layer and for multi-layer. And it's also supporting AQ mode 0, which is the default, and AQ mode 3, which I mentioned earlier, that's used in RTC. So the diagram on the right shows the basic idea. The application, which is here WebRTC or web codecs, using the hardware encoder will first initialize the software rate control interface with all the relevant parameters and encoder configuration. And then during encoder frame by frame, it will input to the software rate control component the spatial and temporal layer ID, the frame type, and then the rate control interface will output a QP And then the encoder will also feed back the encoded frame size, and this goes on frame by frame. So for AV1, there is current work from Intel on integrating this library, this libaom rate control for their hardware encoders. And it's been for VP9 and also VP8 has been actually used already for hardware encoding in meat with very good feedback. Higher FPS, lower delivery time. So here we're going to switch a little bit now to talking about the basic command line we use in RTC and some of the important settings. So on this slide, I just wrote down the full command line, AOM Inc., with all the options. And this is a typical command line for one layer encoding and single thread, one thread in this case. So in the next slides, I'm going to just talk about some of the different settings, what they mean. So the first one is the speed settings. First important parameter is to set the usage equal to 1, which means you're getting real-time mode. And again, as I mentioned earlier, real-time mode will map into a certain set of tools and encoding path that is specifically for real-time encoding. And then there's a speed setting, which is denoted by CPU used, and this controls the quality CPU trade-off. There's speeds 5 to 10 are available currently for RTC. Lower speeds is higher quality, but slower encoding. Speed 5 and 6 are the RD-based mode selection, which is much slower encoding, but much higher quality. And speed 7 and 10 goes through the so-called non-RD encoding path, which is a faster encoding, but lower quality. And also there's several internal speed features that make the encoding faster as you go up and higher in the speeds. And all the speeds in real-time mode use in most 3 path references. And things like the reference selection, the mode search, the motion vector selection, intra-mode search, and so on are all, of course, there's a lot of pruning and that goes on as you go to the higher speeds to get faster encoding. Okay. Additional settings for speed up. So here are a few of the additional settings. There's these cost updates for the coefficients, for the mode, for the motion vector, and these are all, in our case, they're set to 3, which means they're off. We don't update them every frame. There's a bunch of tools that we disable to avoid encoder slowdown. These are enabled. These are listed here: OBMC, warp motion, global motion. We actually have an implementation of warp motion in the non-RD encoding path at speed 7 and above, but it's currently disabled because it's not giving a good speed quality trade-off. And some of these tools are actually not currently in the real-time only build as well. So for the default RTC encoding right now, these tools are turned off. And then there's an additional set of settings to get more speed up that were not listed in the command line. This is to the CDF update mode. The default there is 1, which means you update the CDF every frame, but we have an option to do a frame level selective CDF update. That gives a good speed up with a little bit of quality loss. Do we have a loop filter control parameter where, again, the default is 1, which means the loop filter is never disabled, but we have a mode equal to 3, where we can disable it at the frame level based on the motion content in frame by frame during the encoding. And finally, there's a CDEF parameter. Again, the default enabling CDEF is 1 for RTC. We use CDEF all the time, but there is a mode, I think it's level 2, where we disable the CDEF on non-reference frames, and that's useful for temporal layered coding. Regarding keyframes, although keyframes are disabled for RTC, forced keyframes are often requested in the stream for reasons like there's maybe a new user joins, or there's a big packet loss or resolution change. So for keyframe encoding, the RTC uses a hybrid encoder, which means that the small blocks are encoded through the RD mode selection, and then the bigger blocks are actually going through the non-RD path. And this allows for good quality speed trade-off. There's a number of settings to prune the mode and transform search for the keyframe in the hybrid encoding. These are listed here, and you can get a pretty good speed up, almost 3x speed up with very little quality loss. And you can see all these settings in the open source WebRTC wrapper for AV1 that I provided in the previous slides. So now I want to talk briefly about some comparison numbers to VP9, just to give an idea of the performance. These numbers are somewhat stable for the lower speeds in terms of BD rate, but for the higher speeds, they are in flux, because we're constantly making improvements week by week. So these numbers are a snapshot from early January, and the speeds 9 and 10 in particular are trying to be improved right now. We're actually targeting at least an additional 10% speed up. The reference we use is VP9 with speed 7, because that's a typical default setting used in Google Meet for VP9. So this table shows the low resolution, resolutions like 240p, 180p in SIF. And it shows the average BD rate gain and the speed difference, or the encoder FPS difference, compared to VP9 for speeds 6 to 10. So as you can see, the BD rate gains are larger at the lower speeds, but it's slower, and at the higher speeds, the BD rate gains are smaller, but the encoder is much faster. For example, at speed 9, we can get at least 10% better, close to 10% better BD rate, but we're only about 5% slower than the VP9 setting used in MEET. So again, as I mentioned, speed 9 and 10 are currently being improved. We're targeting probably at least another 10% speed up in the next quarter. The next table is similar, but it's just showing a different test set that involves medium-high resolutions, namely VGA and some 720p clips, so 3060p, 480p, and 720p. Here we're comparing speed 7 to 10 versus VP9 against speed 7 to show the distribution of the BD rate gains and the speed for the different settings. So as example here, speed 10 on this medium-high resolution test set is about 13, close to 14% better BD rate, with about 12% slower. So the next slide, I want to talk about SVC, or layered encoding. The command line and the settings that I've been discussing have been always for one layer encoding. So here I'd like to discuss the layered encoding, or SVC feature, as it pertains to RTC application. So WebRTC uses layered coding for their RTC applications. They typically use up to 3 spatial and 3 temporal layers, and MEET will use layered coding in multi-way video conference calls to better adapt to receivers that have different bandwidth. In AV1, we have flexible support for generating layered structures. There's 2 main APIs for doing this. One is the set SVC parameters, and this is an API, you call it at the init after you initialize the encoder. This will initialize all the relevant SVC parameters. So the number of spatial and temporal layers, per layer parameters like scale factors, maximum QP, the layered target bit rates, the target bit rate per layer, and also the frame rate per layer. And then there's a control called set SVC reference frame config, which is called every frame by the user, where the user can decide or sets a flag for updating any of the 8 reference buffers, and also sets a flag for telling the encoder which of the 7 references are used for prediction. And then there's also a reference IDX that you set for each buffer slot. So this really gives a lot of control to the user, to the application, for generating many different types of layered patterns, layer structures. For the rate control, for SVC, for layered encoding, for RTC, it's very important that you have to respect the target bit rate per layer. So we have this layered CBR rate control mode where we hit the target bit rate per spatial temporal layer. So to evaluate or test layer structures in AV1, there's the AOM encoder is only for one layer. There's currently no interface in AOM Enc to simulate layered patterns. But we have a sample encoder for testing layer structures, which is here SVC encoder art_rtc.c. So I just give an example command line here, where you specify like the number of spatial layers and the number of temporal layers at the command line. And also there's a parameter LM, which is a layering mode parameter, which this maps to a pattern defined in the sample encoder. And there's various patterns up to, again, 3 spatial, 3 temporal layers. At the command line, you have to specify the total bit rate for the stream, and then also the layered bit rate for each spatial temporal layer. There's some other settings the command line did, like the number of threads or the speed and the AQ mode and so on. So in the next slide is an example pattern for one type of layer structure, and this is for 2 spatial layers and 3 temporal layers. SL0, SL1 refers to the base spatial layer, and SL1 is a spatial enhancement layer. And then there's 3 temporal layers here, TL0, TL1, TL2. TL0 is the base temporal layer. You can see that the arrows show the prediction structure. So in this case, there's 1 temporal reference for each frame. And for the spatial enhancement layer, SL1, there's 1 interlayer reference, lower resolution reference. Also, you can notice that the top temporal layer, the TL2 layer, The TL2 frames, in this case, wouldn't update any of the reference buffers because they're not used as a predictor. So that would be a type of what we call droppable frame. And the pattern here is only shown for 4 super frames, if you like, and this pattern repeats itself. So these kind of structures are used in RTC because it provides a way of reducing delay and reducing retransmissions, because if there's packet loss on the temporal enhancement layers, you can sort of drop them and keep decoding the base temporal layer, and then every 4 frames you can come back up. That's why the prediction is like this structure. And the layers can be used to handle different bandwidths for different receivers in a multi-way call. Okay, so AV1 screen share. Here I'd just like to mention screen coding very briefly. We are actively pushing on getting screen content to work really well for AV1 for Meet application. I just want to mention a few comments on this. Screen sharing mode in WebRTC in Meet will pass to the encoder a mode called, for AV1, it's called tune content. And that's set to 1, so that tells the encoder we're encoding screen content. And for this mode, we will have several changes to the encoder in the RTC path for partitioning, for the mode, the motion search, the rate control, loop filter. These are all to get quality and speed improvements specifically for screen. For this application, we're targeting high resolutions, around 1080p type video resolutions. As I mentioned earlier in the talk, AV1 provides new tools specifically efficient for screen coding, and one of them is the palette mode. We're using this in the non-RD encoding path, which is those higher speeds, 7 and above. We can get about like 1.5 dB gains and on some slide changes with text, so it's a very useful tool. Also important for screen share, for screen content, is to react properly when you have slide changes or scrolling to avoid big overshoots. So the rate control, the CBR rate control, will have some logic to react on the slide change to avoid big overshoots. Okay, so in this slide, I just show an example to give an idea of the quality difference that we can expect from the palette mode in AV1 screen content coding. The top and bottom is a slide change with a lot of text. Both are encoded at the same QP, and the top is AV1 without palette predictor, and the bottom is with palette predictor. And the palette mode here is actually similar frame size, but you can see much better visual quality, as you can see here in the image on the bottom compared to the top. So thank you very much for inviting me to give this talk. I hope it was useful for people who are interested in AV1 RTC for their applications, and I hope it encourages people to try out the codec for their applications. My team works very closely with the WebRTC team, and we have a lot of experience in getting RTC video codecs working for RTC. So if you have any questions, definitely ask them in the Q&A, or if not, you can also follow up with me later, and we'd be happy to help you. Thank you again.